Shashank Kalanathy, and today we're going to be going over hands-on machine learning with Scikit-Learn Keras Tensorflow, a book by Aurélien Garonne. This book is considered by many to be kind of like the de facto handbook for machine learning. This is where you get started if you want to learn, which is exactly what I'm doing right now. I'm a data analyst and I'm looking to become a data scientist in the future, and I would like to learn how machine learning works at a deeper level than some tutorials online would take you. Um, so if you're going through this journey with me, you'll know that chapter 2, we put that video out last week where we went through an entire machine learning project from start to finish, and we're doing classification today, which is chapter 3 of the book. So what is classification versus regression? So basically, when it comes to machine learning algorithms, you have many different problems that you can solve. The two biggest ones are probably, well, you have classification and regression. And with regression, you basically have regression is when you're trying to predict values. So for example, if you're trying to predict the revenue that your company will have next year, that is a regression problem. When you're trying to predict the quality of wine, as in good or bad, that is a classification problem. So today we'll be working on classification problems. All right, so before I get started, I do want to let you guys know I do have a Patreon, and all these notes and the code that I'll be writing will be available over there. It is a great way to support me and my work. I put out videos. I try and put out a video about once a week of just stuff I'm doing as a data analyst and the anything that I learn over the course of my studies in the world of data analysis and data science. So if you feel that my work is worth supporting, or you would like to have access to these notes, which I do constantly update, then please let me know, and let's get right into it. So with classification, in this chapter, he spends a lot of time talking about performance analysis, and the reason for that is because with classification algorithms, unlike regression algorithms, performance analysis can be a little bit more difficult because accuracy by itself is not necessarily a great measure of how good a classification algorithm is. And a great example of this is, for example, if you're trying to predict out of 1,000 people, how many people have cancer, let's just say cancer has a less than 99% or has a 1% uh, incidence rate amongst the population, right? If your algorithm just says no one in a population has cancer at all, it is a 99% accurate algorithm, but it's not quite what we're looking for here. So that's why we're going to spend some time talking about performance measures. How do we measure the performance of our algorithm before we actually get started with writing out code for it? So the first thing that you're going to want to do is you're going to want to create something called a confusion matrix. And all a confusion matrix is that it's a matrix that compares every prediction your classifier makes with the true value of that prediction. So what is it? What do I mean by that? It'll come out in a X by X grid. X being the number of classifications that you're outputting. So we're making a binary classifier here, meaning that we're predicting yes or no to something, and binary. There's only two choices. So when you get a confusion matrix output by your algorithm like this, the predicted values will be on the x-axis and the actual values will be on the y-axis. And what does that mean? That means that, for example, over here, 1 means positive or true, and then 0 means negative or false. So that means if you predicted 1 and the actual was 1, it'll show up over here, and that is a true positive. If you predicted 0, negative, and the actual was 0, which is negative, then the value will show up over here. You want most of your values showing up on this main diagonal over here. It goes up and down like this, the main diagonal. And you'll see over here with this algorithm, that I created earlier, that is exactly what's happening. It is going, the main diagonal has the majority of our values. So this is, a decent predictor at least. What everything else is going to be your false positives and your false negatives, basically where you predicted a positive, but it was actually a negative. So you see we predicted positive 1, but the actual value was negative, or we predicted negative and the actual value was positive. That's a false negative. So we want to avoid those. So now that we've created a confusion matrix, and all a confusion matrix is basically you take every prediction that you make and you just put it into whatever bucket it belongs to. You can start running some equations to get precision and recall or sensitivity and an F1 score. And these are basically alternative ways to measure the accuracy of your algorithm. So for example, precision is basically a measure of how often your positive predictions are actually accurate. Now, what does that mean? You'll see over here, the formula is true positive divided by true positive plus false positive. So let's actually illustrate with an example. So you'll see over here, let us make this a little bit smaller. Okay, so we have our confusion matrix over here. Let's do one more thing. There we go. Awesome. Okay, so we have our confusion matrix over here. And as you can see, we've predicted positive, a true positive 789 times. We've predicted a true negative 200 times, a false positive once, and a false positive, a false negative 10 times. Let me go ahead and make this a 51 and then remove 50 predictions from here, so 739. And that I believe should still leave me with 1,000. Yep, 1,000, awesome. So if we wanted to, so first of all, let us go ahead and classify everything as either true positive, false positive, true negative, or false negative. So I'm going to color these over here. I like true positive, so we'll make those green. We'll make this also darker shade of green, true positive. True negative. And then false positive and false negative. So you can see what we have over here. The true positive is cell D4, which is this over here. False positive is right over here, D3. C4 is a false negative, and a true negative is C3. So using that, we can calculate our precision. So what is precision? Precision will be B6, which is what over here, true positive, divided by true positive, plus false positive, 51. So what is that telling us? That's telling us that every time our classifier predicts a positive value, it's only accurate about 93% of the time. Obviously this is a good classifier, but like that would be different from accuracy, for example. I should also probably add accuracy here. So we'll call this one accuracy, and accuracy would be equals the true positive plus the false positive divided by everything else. So it's a very subtle difference over here, but you can see that if I was to like skew the values a little bit more, it would change a bit. So like we're seeing accuracy is at 0.939, but precision is only at 0.935, which is basically telling us that we're mispredicting some of our positive values. We're saying things are positive, but they're not actually positive. Um, Recall and sensitivity is basically the true positive, so 739 divided by 739, which is again your true positive, plus your false negative over here. And then what happens is you can combine these into something called an F1 score. And an F1 score is basically the harmonic mean, which is just another way of calculating a mean versus the normal way you'd calculate means. Um, it is the harmonic mean of precision and recall. And what a harmonic mean does that's different from your regular means is it more heavily biases lower values. Um, And there's a little bit more written about it over here. Oh, okay, I should probably finish my notes over here, but basically gives more accuracy to lower values. And then what happens is you'll eventually run into something called the precision recall trade-off. So how does a algorithm actually classify things into these different categories over here? Well, what it does is it gives a probability to every single classification. And then what happens is that probability, or more than a probability, it gives a value to every single instance in your data set. And then what happens is you can set a threshold gets set. You know, anything that's above this threshold, call that class one. Anything that's below that, call that class zero. Um, and what happens is if you increase that threshold, your algorithm becomes more and more strict, basically meaning it's harder and harder for it to classify things in the positive true class. And if you don't do that, if you lower your threshold, like things are more easily classified as in an accurate manner. So as you can see over here, as you increase your threshold, you are actually you will increase your precision naturally, and you will decrease your recall at the same time. But if you decrease your threshold, you're creating a less precise algorithm, but one that has greater recall. So this is a chart that you'll become very familiar with, and you can use to determine, okay, like what is the threshold we want to set our algorithm at? What's more important, is precision or recall? And depending on what you're looking into, you may decide to pick one or the other. And then I have the code over here, which we're going to be executing on fairly soon. Another accuracy measure we're going to be using is called the ROC curve, or the receiver operating characteristic curve. And it's used for binary classifiers, again, when you're just classifying two different things. And it plots the true positive rate, which is recall, against the false positive rate. Basically, how many times did you predict something to be positive and it actually was positive, versus how many times did you predict something to be positive but it was not positive. Um, and then you'll see the calculation for the false positive rates over here, basically. It's 1 minus specificity. And what happens is you plot the ROC curve against the curve of, I'm not exactly sure what this is called, but this curve is basically if you were to randomly guess. So for example, if you have a binary classifier, the worst predictor you can have is one that would equally predict one class versus another. You know, it's basically randomly predicting. If you have anything worse than that, it's worse than randomly guessing. So you definitely don't want that. So the amount that your curve is above this randomly picking line over here, the better your algorithm is. And you can measure that mathematically using something called area under the curve, AUC. So if the area under the curve is 0.5, it's a completely random classifier. And if it's 1, then it's a perfect classifier. So this is just another metric you can use. So if we want to actually execute and run a classifier, we can go ahead and get started over here. So I think I'm going to be using the wine classifier here. Yeah, we'll be using our own classification task. So we'll be bringing in the wine data set. So, and I'll make that available in the description below. And this is basically a really famous data set that was created by the University of California at Irvine. They have a repository of data sets that are really popular that you can use for your machine learning tasks. So we'll say data import equals pd.read underscore CSV. Oh, you know what? Let me write my boilerplate code first. So all I'm doing over here is I am creating the file path to the file that I want to get to. I think it's called, yeah, it's called wine. So nothing special here. All we did was we imported pandas, you know, the panel data library in Python. We defined our present working directory as the current directory that our file is in. And then we set our file path as basically os.path.join, which basically just combines two things in an OS agnostic way. Present working directory plus wine.csv. And the reason you want to use this instead of what I used to do is because Windows, for example, will use a double backslash for its file paths, and OS 10, Mac OS, will use a forward slash. So that's why we want to use os.path.join. It'll detect your operating system and then just create a file path that's accurate to your operating system. All right, data import. Okay, so we have our data. And as we can see over here, quality on this side over here is what we're trying to predict. So as you can see, quality, and let me actually plot it out over here. So data underscore import quality dot hist. So as you can see, our wine qualities are rated anywhere from 3 to 8. And so we're just going to arbitrarily designate that anything, let's see, above 5, so 6, 7, 8, is a good wine, and anything 5 and below is a bad wine. And that's how we're going to create our classes. Because currently this is a little bit more like well, it's not necessarily a regression problem, but we're going to be creating a binary classifier. So we're going to try and classify wines as either good or bad. So this data set has a bunch of information on it. You know, how much acidity is inside the wine, citric acid, residual sugars, chlorides, densities, and there are actually like mathematical measures you can use to determine, okay, like, is this going to be a good wine or a bad wine? There's some stuff that's just more popular in good wines versus bad wines. So let's go ahead and do our classification task. So first we have to create our classes. So let us say, the first thing we need to do is split our data set into an X and a Y data set, X being what we're going to be using to classify, and Y being what we're actually classifying. So Y equals data import, quality is greater than 5. And as you can see, what that did is that basically creates a pandas series of true or false. True if the value is greater than 5, false if it's 5 or less. And these are our classes right here. It's as simple as that. And then we're going to say X equals data underscore import dot iloc. So basically index LOC, I forgot what LOC stood for, but index LOC. We want all of our rows. So remember for these things too, the normal format is basically your rows go over here, which rows you want go over here, where my cursor is right now, and the columns you want to include go over here, where my cursor is right now. So we want all of our rows. So if I just hit a semicolon, it'll automatically include all of our rows. If I wanted to only include rows 1 through 3, well, there you go. So if I do this, it'll include all of our rows. Okay, then let us import, we want all of our columns up until the last one. And the reason you'll see is, if you see here, the last one is quality. We don't want quality to predict quality, because quality is a perfect predictor of quality. So we need to drop this column, and this is one way to do it. And I'm just hitting Shift Enter on Windows to run the code. So you can see we have all of our columns except for quality. Awesome. Okay. So now we need to do a train test split. Basically, we need to create our training data set and our testing data set. And what happens is we train our machine learning algorithm on the training data set, and then we test it on the testing data set to see, okay, did you actually learn something? And the reason we want to keep training and testing separate is because you want to make sure that you have some way to accurately test how your algorithm will work in the real world. And that's by training it on certain data and then testing it on data it's never seen before, which would be our test data set. We're going to isolate that. You can ensure that your algorithm, or you can predict how your algorithm will work in the real world. So let's go ahead and let us do sklearn. So from sklearn.model selection, there we go, import train test split. And then usually the format for this is xtrain, xtest, y. And if you don't remember this, don't worry. I mean, I've typed this code out so many times that, of course I remember it now. Equals train test split. And then we need to give it our x value. So remember, our x value is just this x we created over here. Our y value, what we're trying to predict, that's over here. So x is what we're predicting with, y is what we are actually predicting, like a normal formula. And then I want my test size to equal 0.2. And then I think random, what is it? Random what? State, that's it, yeah. And all that does is that makes sure that the, for example, if you run this code, if you should get the same train test split that I get if you use random state equals 42. But normally you'd want to use a completely different number, or you wouldn't want to include it at all. And then let's inspect our X train set. We don't want to look at our X test set at all. Cool, so you'll see we went from 1599 rows to 1279 rows, so our split worked. Okay, so the good thing is we have no categorical variables in here, and I picked a data set that had no categorical variables on purpose. That way we can actually that we don't have to worry about encoding those categorical variables. The next thing we have to do is scale our variables. So let's go ahead and do that. So let's see, from Scikit-Learn dot, I think it's pre-processing import standard scalar. And then we need to create our scalar object. So basically that's just going to be scalar equals standard scalar. And then we need to fit our scalar object onto our training set. So we'll do scalar dot fit. We'll fit transform because we also want to transform the data set. X train. I think I can do it like that. Okay, no, I have to actually say scaled. And don't worry about this, I'll explain it in a second. Okay, so what we did over here is we scaled our data. So if you remember from chapter 2, and if none of this sounds familiar, make sure to watch my chapter 2 video. That goes over, we go over all this stuff. Scaling, a lot of machine learning algorithms, especially stuff like linear models, will not work well if, for example, one of your columns goes up to the value of 11, goes anywhere from 0 to 11, but the other values are only from 0 to 1. Basically, it doesn't know how to reconcile those two wildly different scales. One's 11 times the other one. And so what happens is when we scale our values, we bring it all down to the same scale. That way we don't confuse our algorithms. Many algorithms these days will actually do the scaling themselves, but I like to do this just to eliminate that potential for making errors. So what we did is we brought in the standard scalar from the sklearn preprocessing library. We created a scalar object. So basically this variable scalar is a standard scalar object now. And then what happens is we took our X training data and we told the scalar, okay, learn how to scale data based on this data. That's called fitting, when you fit two things together. And then transforming is when we said, okay, now that you've learned how to scale that data, actually transform the data. So what you could also do is you could actually also write scalar.fit X train, which would just fit the two together, but it wouldn't actually transform that value yet. And then you could also write on the next line, scalar.transform X train. But because we want to fit it and transform it, I'm just putting it into one line. And that's how we get our scaled X train value. So as you can see, this is actually the same thing as this data set over here. It's just in a NumPy array format. Which is basically, they're just like data arrays. Basically, it's like just lists of numbers, but they correlate to these values over here. And yeah, we can now get started. It's as simple as that. We should probably also scale our testing data set too. So let's say scaled X test equals scalar.transform. So we don't have to fit it this time because we remember this scalar over here, this object over here, now has memory of how to fit things together, and it's just going to use that memory to transform this data set over here, our testing data set. And then I just want to make sure that it actually formats it correctly. Okay, that looks about accurate. Okay, cool. Now we're going to be running this a couple of times because I'm going to be showing you guys different classifiers. So let's go ahead and let's just, I want to combine all these together into one function. I wonder if I should do that right now or not. Yeah, let's go ahead and do that. So let us call this our pre-processing function, and then you insert an X and a Y. And you'll see a little bit later why we do it the way we do it. Okay, so we do our train test split over there, and then we do our scaling over here. Because we're going to be running this like a couple of different times, like 3 different times, I think. So I want to just make a function for it. That way we don't have to keep typing the same code over and over again. I think that's about it. Okay, so now we just have to return scaled x train, scaled x test, y train, and y test. Sweet. Okay, cool. So now we have our function. We'll come back to it later. We don't need it right now. Okay, so let's go ahead and run a classifier. So I just want to make sure that okay, cool. Our y train is just a bunch of trues and falses. Okay, so I'm going to run a SGD classifier. I think that means stochastic gradient descent. Oh, never mind. We're going to be doing SVM. Okay, so the algorithms aren't particularly important this time. We're going to be going over that in the next chapter where we actually start talking about algorithms. It's just important to know how a classification problem works. So from sklearn.svm, I think, import svc. So what does that even mean? Well, let's go look it up. I actually don't even know what that means. So sklearn.svc, and we should be brought up to the documentation for sklearn. So let me click over here to go up 1 level. Okay, so it looks like it's a support vector machine algorithm. And we go over support vector machine algorithms in a future chapter, but just know that they are a machine learning algorithm technique. And SVC just basically means support vector classifier, I guess. It's just a classification implementation of that algorithm. Okay, cool. So yeah, this sklearn documentation will be your best friend for this kind of stuff. All right, so very simple. Now let's go ahead and create our SVC object, our SVM object, our classifier object. So CLF equals, let's say SVC CLF equals, so SVC classifier equals SVC. Okay, so we've created our classifier object over there. Now we say SVC CLF dot fit, and we want to fit it to our X training set. So we're basically saying, okay, go ahead and look at this scaled X training data, and then go ahead and match it to this Y training data, and try and learn something. Syntax error. Oh, sorry. That doesn't belong there. That's calling a function. I do not want to do that. Scaled X train is not. Oh, did I not? Thought I did over here. Scaled X train is not defined. Oh, scaled X trained. I meant to call that train, but you know what? No. Let's call train. No one ever calls stuff trained. There we go. Yeah, we'll do it correctly. It's really important that you use as much standard language as you can in your code as possible. Okay, cool. So let us go ahead and do some predictions now. Now that we've run the algorithm, now we just have to run some predictions. Okay, so let's say SVC CLF predictions equals, and then what we do is we take our classifier, which we've created. Our classification object is now stored in this SVC CLF variable. So we do svc underscore clf dot predict. We've already fitted it, so it now predict. I know, not transform. It's supposed to be predict, and then we give it x scaled x test. svc. And you see we get this huge array where it actually, that's what it did. It just predicted all the values for us. This is machine learning right here. So now let's go ahead and create a confusion matrix out of it. So from sklearn dot metrics maybe. So from sklearn dot matrix import confusion matrix, and then I think it's just confusion matrix. Come on. And then we need to give it our actual y values, so the y test values, and then let's compare it to our predictions of y test, which will be svc clf predictions. And there's your confusion matrix. So what you'll see, so what we did over here, right? Let's take a step back. We did all our pre-processing, and then we brought in a machine learning algorithm. This is a SVC support vector classifier, I guess is what it means. And we set it equal to SVC underscore CLF. That's so SVC classifier. Then we said, okay, go ahead and take that scaled X training data and then fit it using the Y training data. So go ahead and when you learn how these algorithms work, it'll make a little bit more sense. But basically what we're saying over here is we're saying, go ahead and take that Y training data and then like learn how to actually go ahead and do your machine learning. Learn how this Y training data correlates to all the different numbers you have in the X training data. Okay, you've learned it, cool. That's what fitting is. Then we output some predictions. So we take our X scaled test data, which remember is 20% of our data that we left alone, the algorithm has never seen before. And we say, okay, take your testing data and combine it with take your testing data and use this fit that you've already figured out to try and predict what Y test should be. So we'll compare what Y test should be, what our predictions are, to what Y test actually is. And you'll see we get a classifier that does pretty well. I think there might also be, accuracy score. So I think I can also just type an accuracy score over here and then bring in Y test and that. Oh, I didn't actually run it. So you'll see we're 77% accurate. And then I think you can also bring in precision score. Yep. And then recall score. Awesome. So our accuracy is 77.185 or 1875. Precision score of that 81 precision, and recall score of that 77% recall. So we quickly created all those measurements. You also might be wondering how I created this cool little graph over here. I think this is just matplotlib. So let's say, let's just do it over here. From matplotlib dot or import matplotlib dot pyplot as plt. And then I think it's just plt.math something, mat show. There you go. Okay. Okay, now I was trying to color it a little bit differently. But that you can figure out how to color that yourself later. But I just go ahead and go to Matplotlib and look up like CMaps and stuff like that. Okay, cool. So we've done a couple of our accuracy measures. So, we just ran a classifier pretty quickly and it looks like it performed relatively well. Let's go ahead and see if we can do what we did last time with grid search to improve the accuracy of our algorithm. And remember, grid search basically says, okay, here is a bunch of values. Go ahead and tune our hyperparameters using these values. So grid search is just a form of hyperparameter tuning or hyperparameter optimization. This I'm just going to copy and paste from my code template over here. is it? That's probably near the bottom. Here we go. So we're just gonna run this code over here. And you know what? Let's combine all of this stuff into a function as well. So we'll call this def function, or sorry, let's say def algo accuracy. And then what's all the stuff we need? We need y-test and predictions. Okay, and then we are going to output a confusion matrix. We're going to output an accuracy score. We are going to output precision. We're going to output recall. And I think that's about all we need to do. And then let us return cool. So now we have a function, and we can go ahead and do our grid search, and then we can go ahead and judge how accurately it does. So, okay, from sklearn.model selection import grid search CV, and then these are just parameters from the last chapter. And then let us go ahead and use that same SVC, that same support vector classifier we were looking at earlier. Okay. We need to give it our scaled X train, and then our Y train, and then run it. Okay, so max features is not something that you would include. So you have to actually customize this per estimator. So in that case, let us just go ahead and run it with a random forest in that case. So a random forest is just a different algorithm that we can run. So scaled X train, and then we'll bring in Y train. I don't know why code completion is not working. So let's go through what this is over here. So basically, this is a grid search. So what a grid search is going to do is it's going to search through all of these parameters, these hyperparameters for the machine learning algorithm you're talking about. So if you saw earlier, actually, because SVCs don't have, I think it was like max features, the grid search errored out because it didn't know what to input for the SVC. So instead of going and looking at what is inside SVCs and everything, which I think is just distracting for the point we're trying to make right now, we'll just run a random forest classifier, which will probably get us a better result anyways. So we're now going to grid search across all of these parameters over here. And I think that's all we need to do. And then I need to actually import the random forest classifier. So I think that's in learn.ensemble import random forest classifier. So you'll see it's running right now. And basically what it's doing is it's inputting all these different hyperparameters into the random forest and trying to maximize for this accuracy metric right over here. All right, so now we have all of our data stored inside something called grid search. So we can type in RFC CLF, so random forest classifier, I guess, equals grid search. As you can see, my code completion is just brilliant. Doesn't do anything. Grid search dot I think it's like estimator or something. Yeah, best underscore estimator underscore. And what this will do is this will actually give us the estimator that got us the best results. So, okay, it seems that when your maximum features is 2 and your n estimators is 30, that's your best algorithm. So now, I believe it's already been fitted. So let's go ahead and output our prediction. So RFC underscore predictions equals, and then what do we do over here? We bring in our RFC underscore CLF classifier dot predict, and we wanted to predict using the scaled X test data. Awesome. Looks like we came out with a bunch of good predictions. Now let's go ahead and run this on our algo accuracy. So algo accuracy, and then we need to give it our Y test and our RFC predictions. There we go. We have our accuracy, precision, and our recall along with our confusion matrix over here. I don't think we did significantly better than our support vector machine. Oh, we did. Yeah, yeah. The precision score was definitely better. Accuracy of 77. We got 79 over here, rounded up to 80. Um, and it seems even our recall might be better. 77 over here, 79 over here. Awesome. So we have an algorithm that is more has better accuracy, recall, and or precision and recall. Awesome. So and random forest like oftentimes will work better than support vector algorithms. Cool. So that's a binary classifier over there, fairly simple. And through a binary classifier, you can make almost anything. Or binary classifier. So we've done a binary classifier which is classified wines as either good or bad, and we got some pretty decent accuracy rates from that, which is pretty crazy to think that just with some information, basic mathematical information on a given wine, that you can predict that kind of stuff. You then have a couple of other classifiers. So you have something called a multi-class classifier, which is basically a classifier that allows us to classify instances into one of multiple different classes. And there are two basic strategies to doing this. So you have the one versus rest or one versus all. And what a multi-class classifier is basically saying, like, for example, what if we wanted to classify our wines into good, better, best? So, 2 and 3 are good, or sorry, are good. 4 and 5 are better. And 6 and 7 and 8 are best. That's where you could use a multi-class classifier, which there are a couple of ways to handle it. Basically, you will create a bunch of binary classifiers. That's one, where you train a classifier for every class you want to predict. So, for example, you train a classifier to classify, goods, and a classifier to classify betters, and a classifier to classify bests. Basically just three different binary classifiers. Or you can do one versus one, where you train a classifier for every pairing of classes. Okay, so if I'm given a one and two, like have a classifier predict which one it is. Is this instance a one or is it a two? Is it a two or is it a three? Is it a three or is it a four? Um, and when you have less efficient algorithms, such as support vector machines, for example, you want to do one versus the rest or one versus all, because those tend to be a little bit faster. And because you are running fewer iterations of the algorithm. Next, you have something called a multi-label classifier. And a multi-label classifier is basically a classifier where you are going through different you're trying to apply more than one label per group. So for example, maybe you want to predict the alcohol content and the quality of the wine, two different measures. And the good thing about this is that you can run it basically like you would a binary classifier, and then just run accuracy measures on how well did it predict alcohol and how well did it predict quality. Because the only thing that'll work, or sorry, things like a confusion matrix and precision and recall won't work when you have different multiple sets of values that you're trying to predict at the same time. And I go over this in my notes in a little bit more detail. And then you have something called a multi-output classifier, which we're not really going to go over, and he doesn't give us too much detail in the book either. So that's really all he went over in chapter 3. I think he goes into significantly more detail in further chapters. Chapter 3 was a bit of a short one. I have a little bit of further reading over here talking about why even though he uses MNIST, a lot of people are saying that MNIST shouldn't be used anymore. And this is for learning purposes, so it probably doesn't matter. And that's why I decided to use a wide data set. And so that's about it for today for classification. I wanted to keep this video a little bit shorter in order to, just get through it a little bit faster so I can get started on chapter 4, which is going to be a doozy. Chapter 4 is significantly longer. So if you like what you saw, if you could please like, comment, subscribe. The likes and the subscriptions especially really, really help me out. I think if I get enough subscriptions, then maybe someone will come and sponsor the videos, which will make this a lot easier for me to make more and more videos for you guys. If you really like my work, if you could subscribe to my Patreon, that would be awesome. I'm looking at potentially starting a Discord chat with the people in that Patreon, but I haven't confirmed anything yet for that. But thank you guys so much for your time, and I hope you have a great day.